The mathematical tools that we require to do hypothesis testing or to form confidence intervals always seem quite similar to one another. We use a lot of the same concepts, whether we're working in hypothesis testing or we're working with confidence intervals. And this is not really a surface level agreement between these two different concepts. This is actually something that is sort of more fundamentally true. It turns out that the mathematical foundation that we build off of to form confidence intervals and the mathematical foundation that we build off of to do hypothesis testing are really one and the same. And because of that, if you have confidence intervals, then in a sense, you also have hypothesis tests. So the mathematical foundation for hypothesis testing and for confidence intervals is shared, and as a result, every confidence interval that you form contains a hypothesis test within it. So how can we think about confidence intervals as hypothesis tests then? Well, when a confidence interval is formed for some specific level of significance, this is going to give us an interval that contains the truth with a set probability. By definition, a confidence interval gives us an interval that we know is going to have the true parameter in it at some set probability. Now, for sake of example, we can suppose that we have a symmetric confidence interval that's being formed for the mean. So we know that the way that this is going to work is we're going to take the sample mean and then we're going to add and subtract off the margin of error on this. Now, imagine that some specified value, right, so perhaps we think it's the true value, actually falls within that confidence interval, right? And so what is the setup that we have going on here, right? So we're taking x bar here. We go down some amount to get the lower bound, which I will just call A. We get up some amount, which I will call B, right? That's our confidence interval. And what we're saying is that suppose that we have some value, which I will just call X here, that actually falls within this interval. Okay. Now, if this interval had been formed centered on this specified value rather than on the sample mean itself, that must also contain the sample mean. And so what do we mean by this? Well, we have some distance right here, right, which we call our margin of error. The same distance occurs right here, the margin of error. And so the point is that if we go the margin of error down and the margin of error up from x, we're going to get a different interval, right? So we have this being our margin of error here, and we have this being our margin of error as well. But the key point is that x bar here is going to fall within this interval, right? So their intervals are going to overlap. This has to be the case because of the symmetry of the interval, all right? And so what does that actually mean for us? Well, if the specified value, if that x value we had on the diagram there is actually correct, then the probability of observing something more extreme than the sample mean is at least alpha, right? Because we know that the probability of observing something outside of the confidence interval is alpha, right? A confidence interval, if we go A to B here, then observing anything outside of here is going to happen with probability alpha, right? That's sort of our setup of the confidence interval here. And so then if you're outside of that confidence interval, you have to have probability alpha of things being observed. Okay. And so because the sample mean is within the confidence interval, then we know that there's at least an alpha probability that something more extreme was observed. And so if you think about testing the null hypothesis, and in our case, it would have been, say, the null hypothesis that mu is equal to x, right? That value that we specify, right? Then the sample mean is not going to be sort of extreme enough to reject this null hypothesis, right? So if you think about testing that, then under the null hypothesis, we would fail to reject at the level of significance. Now, this is because there's a greater than alpha chance of observing something more extreme, and by definition in hypothesis testing, if there's a greater than alpha chance of observing something more extreme, then we fail to reject the null hypothesis. So outside of the interval is exactly alpha, that's more extreme, but the sample mean is within the interval. And so therefore, the sample mean is not extreme enough to be considered to reject the null hypothesis. Okay, so that's sort of the intuition or the build-up of the idea of how we can think about confidence intervals as hypothesis tests. But we can make this slightly more concrete. So how do we actually go about testing the procedure? If we're given a two-sided confidence interval with a 100 times 1 minus alpha confidence level, then in order to test is theta equal to theta naught versus the two-sided alternative at the alpha level of significance, all we have to do is check is the value of theta naught contained within the interval or not. Okay. If it is, we fail to reject the null hypothesis at the alpha level of significance. If it's not in the interval, then we do reject the null at the alpha level of significance. Okay. So in order to use a confidence interval to test a hypothesis, all you have to do is check, is the null value inside of the interval or is it outside of the interval? If it's inside the interval, then you fail to reject the null. If it's outside of the interval, then you reject the null. We can use one-sided confidence intervals to run one-tail hypothesis tests using the same technique. So if you have an interval that has just a lower bound, a up to infinity, then what you're doing is you're testing the null hypothesis that theta is greater than or equal to theta naught. And you do this by checking, is theta naught inside of that interval? If you have the upper bounded interval, right, so from negative infinity up to b, then you can test the null that theta is less than or equal to theta naught by checking if the null value is in the interval. Okay. So in some sense then, confidence intervals are containing all of the information from a hypothesis test. If you want to do a hypothesis test and you have a confidence interval, as long as those levels of significance match, then you have the same information contained in both. This can be a very useful reason for reporting confidence intervals, because then you get the confidence interval, which contains information on the uncertainty, but you also implicitly get a hypothesis test. Okay? So if you are actually trying to communicate scientific results here, confidence intervals contain lots of information, including information about the hypothesis test. So let's look at some examples here. In each of these examples, we're going to be given a confidence interval, and then there's a hypothesis test that we want to test. And what we're going to try to do is run the hypothesis test or explain why the confidence interval does not allow us to run the hypothesis test. Okay, so let's take a look at our first example here. Right, we are told that we have a 95% confidence interval, okay? And the 95% confidence interval is found to be -7 up to 3. Right? So it's 95%, -7 up to 3. We want to test, is the null equal, or is the theta equal to -11 at alpha equals 0.05. Right? And so in order for us to test at alpha equals 0.05, then what we would need is a 95% confidence interval. Okay, and so to run this hypothesis test, because we have the correct confidence interval here, it's as simple as checking, is -11 inside of this interval here? And because -11 is not inside of the interval, then we're going to reject the null hypothesis, right? And so since -11 is not in the interval, we reject the null hypothesis at the alpha equals 0.05 level of significance. Let's take a look at our next sort of example here. So we have this time a 90% confidence interval. It's found to be -2 up to -1. We want to test, is the null equal, or is the parameter equal to 5 at the 1% level of significance? Okay, so what could we actually learn from this confidence interval, right? So the idea is that, well, if we're testing this null hypothesis, right, we know that -5, or that 5 is not in this interval. Right? 5 does not fall between -2 and -1, and so we could reject the null hypothesis at the alpha level of significance, which in this case is going to correspond to alpha equals 0.1, right? Because we have 1 minus 0.9 equals 0.1, and so then if we take alpha equals 0.1, then we can reject the null hypothesis. So the first thing to note is that we could reject the null hypothesis, but we'd be rejecting it at the alpha equals 0.1 level of significance. Right? However, this doesn't tell us anything about what to do at 0.01, right? Because we're increasing the confidence threshold here, right? We would need to have a 99% confidence interval. And so even though we reject at alpha equals 0.1, we don't know what we would do at alpha equals 0.01. And so this confidence interval does not give us that information. So we cannot draw conclusions for alpha equals 0.01. We can look at this 99% confidence interval. It's -9 up to 16. We want to test, is the parameter equal to 15 at the 1% level of confidence here, level of significance rather. In this case, 15 does fall inside of this interval, right? And so because it's inside the interval and we have agreement between the confidence level and the alpha, then we fail to reject the null. So since 15 is in the interval, we fail to reject the null. Now we have this 90% confidence interval. It's found to be -10 to -3. We want to test is the parameter equal to -7, and we want to test this at alpha equals 0.05. So again, here we have a misalignment, but this is actually going to be a slightly different case, right? So the first thing that we can directly say based on this is that if we take alpha to be 0.1, right, then since theta is in this interval, right, -7 falls between -10 and -3, then we fail to reject at the 10% level of significance. Okay, so we're failing to reject at 0.1. Now, because we fail to reject at 0.1, we're also going to fail to reject at 0.5, right? Or at 0.05, rather. Because if you are failing to reject at the 10% level of significance, then what that means is that your p-value is above 10%, right? And if your p-value is above 10%, right, so we have found that p is greater than 0.1. In order to run the hypothesis test at the alpha equals 5, we want to know, is p less than 0.05? But of course, we already know that p is greater than 0.1, right? And so we can say, well, no, this is not the case. And so as a result, we're going to fail to reject at alpha equals 0.05 as well. Okay, and so in this case, even though we're given a 90% confidence interval, we can still get the result of a 5% level of significance test. Okay, so we also fail to reject at alpha equals, 0.05 would be sort of the question here, but 0.01 also works, right? We're going to fail to reject at everything below the alpha that we're actually given here. Now, suppose we have a 95% confidence interval. It's found to be 7 to 9. Is theta equaling 5 at the 10% level of significance? So once again, if we're testing this at the 5% level of significance, it's easy enough. We would say, well, is theta equal to 5? No, we're going to reject the null hypothesis. Okay, so we can reject the null hypothesis at alpha equals 5 here, right? But then what can we say at alpha equals 0.1? Well, if you reject the null hypothesis at 0.05, then we know the p-value is less than 0.05, right? So we have p is less than 0.05, right? What we want to know is p less than 0.1? And the answer is going to be yes, right? Because we know it's less than 0.05. And so in this case, we can also reject the null hypothesis at 0.1. So the thing that I want to highlight here, right, if we think about this example B and then we think about example E, what is the difference? Well, in the first, we have a 90% confidence interval, right? We're rejecting the null here, but we want to test at a more significant level of significance, and so we can't say anything. In E, we also reject the null, but if we want to test at a lower level of significance or a less significant level of significance, right, then that's totally fine for us to do. So you can always move alpha in one of the directions, depending on whether you have failed to reject or whether you have rejected. Let's take a look at a few other examples here. So we have a 90% confidence interval. In this case, we're testing 4 up to infinity, right? And we want to test, is the null greater than or equal to 3? Okay. So our alpha is aligned with the 90%, and so is the null hypothesis with the interval, right? The interval is 4 to infinity. The null hypothesis is that it's greater than or equal to 3. Because 3 is not in this interval, then we're going to be able to reject the null hypothesis here, right? So since 3 is not in the interval, we reject the null hypothesis at alpha equals 0.1. Now let's suppose that we had a 95% confidence interval that is going to be negative infinity to 2, right? We want to test, is the value less than or equal to 0 at alpha equals 0.05. So once again, 95 lines up with alpha equals 0.05, so that's totally fine. We have this upper bounded confidence interval here, right? And we want to test the lower null, so that's all in agreement. So then we check, is 0 in this interval? 0 is in fact in that interval, right? And so then we can fail to reject the null hypothesis at the level of significance. Now we have a 99% confidence interval found to be 8 to infinity, right? And so we have this, again, lower bounded version here. Alpha aligns with the level of significance. However, the important piece to note here is that we want to test this lower bounded null, or sorry, this lower tailed null. And in order to test the lower tail null, what we need is an interval that goes from negative infinity up to some positive value, rather than having 8 up to positive infinity. And so this interval does not allow us to directly test this null hypothesis here, okay? Because in order to test this null hypothesis, we need the upper bounded interval, right? So you need the interval that aligns with your null hypothesis in a sense. And so here we're not going to be able to say anything, right? Because we can't use this for the specified hypothesis. Last example here, 90% confidence interval, -8 up to -4, right? The 90% aligns with alpha equals 0.1, so that's all fine, but we want to test the upper null here, right? And we have the wrong interval to do that. In order to test is theta greater than or equal to some value, you need the lower bounded confidence interval here. And so once again, we're not going to be able to use this interval to test the specified hypothesis. Okay. So if you have confidence intervals, then you also have hypothesis tests, right? Hypothesis tests and confidence intervals are motivated through different concerns. However, the underlying mathematics that they use are equivalent. And so then every confidence interval implicitly contains a hypothesis test. And so by reporting on a confidence interval, then we can also perform set hypothesis tests. This is going to be a critically important use case for confidence intervals, and it's also a really strong motivation for reporting confidence intervals. The main thing to watch out for is that you can only test certain hypothesis tests using these confidence intervals, right? And sometimes we're going to be able to move from one level of significance to another, depending on the conclusions that we're drawing. If you're working in the one-tailed case, then you want to make sure that you're using the correct confidence intervals to test the hypotheses that you're actually interested in, rather than taking the wrong-tailed for that. But in the event that you have the confidence interval that aligns with the test that you care about, because the mathematics are the same, any conclusions that you draw from the hypothesis test are implicitly contained within that confidence interval, and that's going to go a long way to improving the utility of confidence intervals.